So this problem says that a Ferris wheel is 20 meters in diameter and boarded from a platform that is 5 meters above the ground. The 6 o'clock position on the Ferris wheel is level with the loading platform, and the wheel completes 1 revolution in 2 minutes. How many minutes of the ride are spent higher than 24 meters above the ground? Include at least 3 decimal places in your answer. So the first thing I'm going to do is draw a diagram of what this situation looks like. So the Ferris wheel is 20 meters in diameter. So I'll draw a circle where the distance from the top of the circle to the bottom of the circle, which would be the diameter, is 20 meters. And while I'm at it, since the radius is half of the diameter, that means the distance from the middle of the wheel to the top or the middle of the wheel to the bottom is 10 meters. Now the problem says that the wheel is boarded from a platform that is 5 meters above the ground and that the 6 o'clock position on the Ferris wheel is level with the loading platform. This is just in my opinion, slightly confusing way of saying that the bottom of the wheel is 5 meters above the ground. Because when they talk about the 6 o'clock position on the wheel, they're referring to the face of the clock, where the top would be 12, the sides would be 3 and 9, and the bottom would be 6 o'clock. So saying that the 6 o'clock position of the Ferris wheel is level with the loading platform is the same as saying that the bottom of the wheel is at the loading platform, which is then 5 meters above the ground. They also tell us that the wheel completes 1 revolution in 2 minutes. Well, 1 revolution means that is the period of the function. So the period will be 2 minutes. And then we're asked to figure out how many minutes of the ride are spent higher than 24 meters above the ground. So the first thing that I will do for this problem is create a mathematical model for the position of a passenger t minutes into the ride. Now I know that to do this, I'm going to want to use a sinusoidal function, meaning some sine or cosine function, because if we were to do multiple revolutions around this wheel, the passengers would go up and then down and then up and then down and then up and then down again, just like an oscillating sine or cosine curve would. So the first thing I want to decide is what will my base function be? So base function is what I use to refer to what function am I transforming to get the position function for this specific situation. And I like to think of it as having 4 choices. Now we really only have 2 base functions to work with, the first being the sine function and the second being the cosine function. And we're really just transforming one of those 2, but I think it's helpful to think of the vertical reflections of these functions as like their own option. So I have y equals sine of x. If I reflect that vertically, I will get the graph of y equals negative sine of x. And if I reflect the graph of cosine of x vertically, then I get the graph of negative cosine of x. And the key things I'm looking for on these base function options is where do they start? And by start, I mean where is the function on the y-axis and where do they go from there? So what I mean by that specifically is that if I look at my y equals sine of x graph, it starts at the midline and then it goes up. So if I start looking at x equals 0 on the y-axis, I'm at the midline of my sinusoidal curve and it increases initially as x increases. So it goes up as we move to the right. Contrast that with the y equals negative sine x, which still starts at the midline, but it goes down first. So it's decreasing as x increases initially. Neither of those graphs are going to be what I choose here for the Ferris wheel example, because my passengers aren't starting at the middle of the wheel, the middle height. They're starting at the bottom. So I can eliminate the sine functions as options here if I want to choose the simplest possible way to do this problem. When I look at my cosine graphs, I can see that y equals cosine of x actually starts at the maximum, which also won't work here because we don't start the passengers at the top of the wheel. They get on the wheel at the bottom. But if we finally look at our y equals negative cosine graph, that does start at the minimum. It has a local minimum on the y-axis, and that is what our graph should look like, because the passengers, again, start the ride at the bottom of the wheel, so we want the trig function that starts at its minimum. So that means that we're going to use y equals cosine with a negative coefficient. So when I go to write my function, h of t, the height of the passenger above the ground, after t minutes, I'm going to guarantee that I have a negative out front, and then I'll let a be my amplitude. In general, a itself is not the amplitude. The amplitude is the absolute value of a, but because I'm building the negative sign into my formula, now a really will be my amplitude. And then typically this is cosine of b t minus c plus d. And the other way that this is sometimes written that's also really useful is sometimes we'll do cosine of b times parentheses t minus some number, which I'll use a Greek letter phi. And there's a really important distinction to make between these two options. And that distinction is with regards to the phase shift. In the first version, where there's no parentheses inside, so it's bt minus c with no parentheses inside the cosine function. In this format, the phase shift is not the number c being subtracted. It is c divided by b. In contrast, the second option where I have b times parentheses t minus phi, so essentially the b has already been factored out. In this format, the phase shift is phi. This goes back to how transformations of functions work, but one way you could convince yourself that these really are equivalent is if you took the bt minus c form without parentheses and you factored out the b to make it look like the second option. Factoring is essentially like dividing. So you would end up with t minus c over b in the parentheses. So the phase shift phi in the form b times t minus phi, phi is c over b, which is why if it's not factored, we just calculate the phase shift as c over b. But if it is factored, then we just pull the phase shift directly from whatever is being subtracted from t, because again, the coefficient b on t has already been factored out. It's a really subtle difference, but it's an important difference. That being said, it's not actually important for this problem because in this problem, we don't need a phase shift at all. As our graph of negative cosine shows, we are starting right at the bottom, and that's exactly where the passengers are starting. So there's no need to do any sort of phase shift because it already matches up perfectly on the y-axis for the starting point. So in both of these cases, the phase shift will be 0. So we can say that h of t will be negative a times cosine of bt, close parentheses, plus d. Now to find the other values, a, again, because I already wrote the negative out front, a is the amplitude in this case, and there's lots of ways to think about what the amplitude is. The way that I typically think about it is it's the distance from the max to the midline, and we can see from our diagram of the circle that the top of the circle is the max height. The horizontal line through the center of the circle is the midline height, And the distance between those is by definition the radius of the circle. So my A value, which is my amplitude for this problem, will be 10. The other way that you can figure that out is you could use the formulas that the amplitude is also the distance from the midline to the minimum, which will be the radius of the circle again, or you could do the maximum minus the minimum over 2. But the distance here between the maximum and the minimum is the diameter of the wheel, which is 20 meters, and you divide that by 2 and you get 10 meters. So no matter how you choose to figure it out, the amplitude is 10 meters for this problem. And again, because I built the negative into my formula, that means my coefficient on cosine is -10. Next, I need to figure out the value of B. Now, B is not the period. Sometimes people get confused and they think that B is the period of the function, but it is directly related to the period. The relationship between B and the period is that B is 2 pi over the period. So 2 pi over 2, so pi. So now I have that my h of t function is -10 cosine of pi t plus d. And the last thing for me to figure out is what is the midline of my function, because the d is telling me the vertical shift. For an unshifted sine or cosine function, the midline would be 0. So if our midline is higher or lower than 0, then we need a vertical shift to show that. And in our problem, we can see from our diagram that the center of the wheel is 15 meters above the ground because we have the 5 meters for the platform plus the 10 meters for the radius of the wheel. So D is 15. The other way you could figure out D is it's always the average of the max and the min. So we could do that D is max plus min over 2, which in this case, the maximum is 25 meters, the diameter of the wheel plus the height of the loading platform, and the minimum is the height of the loading platform. So that's 25 meters plus 5 meters divided by 2, and 30 divided by 2 is 15. So either way, we end up with the same formula for the height above the ground after t minutes. H of t equals -10 cosine of pi t plus 15. Now we're not nearly finished. This was just the first phase of the problem, but it's a really important phase where we create the mathematical model. Now we get to use that model to answer questions. And this problem specifically wants to know when the height is higher than 24 meters. Now you should not be answering this with solely a graphing calculator. You need to be able to show how to use trigonometry to answer the question. But that's not to say that a graph is not helpful. So I'm going to make a rough sketch of this function to help me understand what I'm looking for and why, and also to give me a check on my answers to see if they seem reasonable. So the way I like to make my graphs of transformations of sines and cosine functions is I first like to draw in the midline. So our midline is at 15 meters. So I'll draw a horizontal line at height 15. And then from the midline, I use the amplitude to find where the max and the min would be located. So the amplitude is 10 meters. So if I go 10 units up from the midline, I reach the maximum, which will be at 25. And if I go 10 units down from the midline, I end up with the minimum, which will be at 5 meters, which again all matches up with what we saw in our diagram. Then the period of this function is 2 minutes. So I'm going to label my horizontal axis, which I have units of minutes. I'm going to label it from 0 to 2. And because I know that the important features of a sine or cosine graph happen every 1/4 of a period, and 1/4 of 2 is 1/2, I'm going to label my axis in increments of 1/2, or in decimal form, 0.5. Now, when I go to sketch my curve, we know it starts at the bottom. So on the vertical axis, so t equals 0, I have height 5. Then Then a quarter period later, so half a minute later, we will be up at the midline. Then another quarter period later, we'll hit the max, and then we reverse it on the way down. Another quarter period later, 1.5 minutes, we hit 15 meters again, the midline. And then finally, after 2 minutes, we are back where we started at the minimum height of 5 meters. And then I can sketch in my cosine curve. And the question is asking for when the height is above 24 meters. Now, this is not going to be a perfect picture because it's not a perfectly to scale graph, but I'm going to estimate where the horizontal line at height 24 would be, and then see that that intersects my cosine curve in 2 spots, which I'm going to call those times where the intersection points occur to be T1 and T2. So I have one intersection point between 0.5 minutes and 1 minute, so just before the maximum is reached. And then I have another intersection point between 1 minute and 1.5 minutes, so just after the maximum is reached. What I'm interested in is really the time in between, because that's when the graph is above the horizontal line at height 24. So there's more than one way to do this, but the way that I like to do it is find the 2 times where it's equal to 24 meters and then subtract them. So the time spent above 24 meters will be T2 minus T1 once I find those times. The other way that people often do this that also works is they say, well, if I look at my graph, it is symmetric about the vertical line through the maximum, which means if I could just figure out how long it takes to go from 24 meters to the maximum, which would be 1 minus T1 in this case, because the max occurs at 1 minute and we first hit 24 meters at T1. So the difference between those 2 times is 1 minute minus T1 minutes. Then it has to be the exact same amount of time to come back down. So instead of finding T1 and T2 and subtracting them, you could take the time that the max occurs at, so I'll call that T sub max here, and subtract the first time and then double it, because it takes just as much time to go down as it does to go up. And again, specifically for this problem, that would be 1 minus T1 times 2, because the maximum is reached at 1 minute. You can do it either way. Both are totally fine. Now, to do it in either of these methods, I do need to find at least one time. So that's where the trig equation comes in. So we have our formula for h of t, negative 10 cosine pi t plus 15. And we want to know when that is equal to 24 meters. So we set it equal to 24. Now, in any trig equation where there's only one term with a trig function in it, the first thing you're going to want to do is isolate that trig function. So for this problem, I subtract 15 from both sides first to get 9 equals negative 10 cosine of pi times t. And then I divide both sides by negative 10 to get that negative 0.9 equals cosine of pi t. From here, I highly recommend that you use a technique that's very common in math called substitution. So rather than work with cosine of pi t, I'm going to substitute, meaning replace that expression with a new expression that's simpler. So I'm going to call pi t theta. When I do that, my equation becomes the cosine of theta equals negative 0.9. The reason I like this substitution method is it can prevent you from making common mistakes when trying to find the second time. And I'll talk about that more when we get there. But that's really the purpose of this, is to avoid the temptation to do things that are incorrect. Now, ignoring the context of the problem for a little bit, if I was just looking to solve cosine of theta equals negative 0.9, I want to think about where those solutions will be located. So if I'm looking for the solutions between 0 and 2 pi, this equation will have two solutions on the interval 0 to 2 pi. And because cosine is negative in quadrants 2 and 3, because cosine corresponds to the x-coordinate, and the x-coordinate is negative when we are to the left of the y-axis, I know my two solutions are in quadrant 2 and quadrant 3 when I'm limiting myself to 0 to 2 pi. I can find my first solution using the inverse cosine. I really have to use the inverse cosine because negative 0.9 is not one of the x values from our unit circle common angles. So I'm going to use the inverse cosine function to find my first angle. And because the inverse cosine only can output between 0 degrees or 0 radians and 180 degrees, so pi radians, I know my inverse cosine can only give me angles in quadrant 1 and quadrant 2. So because the output of the inverse cosine has to be in quadrant 1 or quadrant 2, but I know my solutions are only in quadrant 2 and quadrant 3, I can be 100% sure that my first solution, the one I'm getting from the inverse cosine, is in the only quadrant that meets both of those conditions, quadrant 2. So I'm going to sketch in my first solution, theta 1. Now to find my second solution, there's a couple ways to think about it, but one way is to use reference angles. So the reference angle for theta 1, because theta 1 is in quadrant 2, its reference angle is pi minus theta 1. So what angle would I have to add to theta 1 to make it all the way to pi? Or how much before pi did I stop? So it's the angle between the terminal ray of theta 1 and the negative x-axis. Whatever my theta 2 is, I know it's in quadrant 3, and for it to have the same cosine, it has to have the same reference angle. But now, because theta 2 is in quadrant 3, the reference angle is telling me how much further past pi I have to go. So theta 2 is pi plus the reference angle, which is pi minus theta 1, making my theta 2 2 pi minus theta 1. So 2 pi minus the inverse cosine of negative 0.9. The other way that you could think about why theta 2 is 2 pi minus theta 1 is instead of viewing the theta 2 angle that I drew as a positive angle initially, we could think of it as a negative angle, in which case it would have been negative theta 1, because it's exactly the same size as theta 1, only we're going clockwise instead of counterclockwise. But then we don't want a negative angle. We want angles between 0 and 2 pi, so we can take the coterminal angle to that by adding 2 pi onto it. And either way, you end up with 2 pi minus theta 1. And this is a general rule that you can use anytime you have an equation with cosine in it. The first angle will be the inverse cosine, assuming you've isolated the cosine function, and the second angle will be 2 pi minus the inverse cosine of whatever the number is. So for this problem, the inverse cosine of negative 0.9 is approximately 2.690566. I'm keeping a lot of digits because I want to make sure that I don't inadvertently round too much too early in the problem, which could make my final answer off by enough that something like WAMAP would not accept it. Or if I was actually trying to use this for something, maybe I would be outside of the tolerance of whatever application I was using it for. And then if I do 2 pi minus the inverse cosine to get my theta 2, it is approximately 3.592619. Now, these are not our answers because these are not times. These are angles. To get the times, we have to use our relationship that theta is pi times t. So if you divide both sides by pi, t is theta divided by pi. So I can take each of these two angles that I found and convert them to times by simply dividing them by pi. Now, other problems are sometimes more complicated. If you have a phase shift, then you'll have to deal with that as well. But here we had no phase shift. We just had the pi that represented the period being 2 minutes instead of 2 pi radians. And so this is the only step we have to take. So my time 1 will be my theta 1 divided by pi. So if I take my inverse cosine of negative 0.9 that I wrote down and divide that by pi, I get that my first time is 0.85643 minutes. And now the reason why I think it's so important that I did the substitution and I found two angles first is because what I see so often is people try to find their second time by doing 2 pi minus their first time. But that's incorrect because 2 pi is an angle in radians and T1 is a time in minutes. They're not even the same kind of thing. That would be like saying that you were going to subtract 5 apples from 30 feet. What do you even mean? Like, what does it mean to subtract apples from feet? I don't know. They're not the same kind of thing. One's a measurement of length and the other one is apples. So always make sure that when you are adding or subtracting things in an application problem, that they are the same type of thing. They don't have exactly the same units. You really shouldn't be adding or subtracting them. But this is a really tempting thing to do if you didn't do the substitution and you found your first time and you said, okay, I know I need a second one. I know the rule for inverse cosine is I do 2 pi minus, but it has to be 2 pi minus the angle, not 2 pi minus the time. So instead, because we already did the 2 pi minus, because we did our substitution, we can just take our theta 2 and divide it by pi. And when we do that, we get 1.14356 minutes. And then finally, to find the time spent above 24 meters, we subtract these two times. And the problem said to round to 3 decimal places, so my final answer is 0.287 minutes. Before I end the video, a few things to look at. First, does this answer even make sense? Do the times I found make sense? Well, because I have the graph, I can see that my first time was supposed to be between 0.5 minutes and 1 minute, and I got 0.8 minutes and change, so that makes sense. And my second time was supposed to be between 1 minute and 1.5 minutes, and I got 1.14-ish minutes, so that also makes sense. So at least my times I found were reasonable. And the last thing I want to check is that our alternate method that uses the symmetry of the graph also gets the same answer. So remember that because the graph is symmetric about the vertical line through the maximum, if we could just find the time it takes to go from 24 meters up to the maximum, we could double that to get the total time above 24 meters. So specifically, we're looking at the time at which the maximum occurs minus the first time we reach 24 meters times 2. We know that the maximum occurs at 1 minute because we made our graph and we could see that. And our first time was 0.85643 minutes. And so if we do the subtraction and then double the result, we do in fact get the same answer, 0.287 minutes. However you choose to approach these problems is up to you. Relying on symmetry from the graphs is a wonderful way to approach these problems. I would just highly encourage you that if you choose to use that method, that you do always draw out the graph, because things that seem very simple in this example where there's no phase shift can get a little bit complicated when there is a phase shift. That's not to say that you can't use the same types of symmetry arguments. You absolutely can, but you have to take the phase shift into account when you do those. So drawing a sketch of the graph, it does not have to be perfect, but enough to incorporate the phase shift so that you can see what values you should be subtracting from each other is very important to make sure you execute that strategy correctly. If you choose to use the first method I showed you where you find the two angles and then convert them to times, then you don't have to worry about the phase shift affecting your logic. The process will be exactly the same. All the phase shift will do is add one more step to the process of going from the angles to the times, but otherwise everything else will be the same. So use whatever clicks the best in your brain, and I'm just recommending that you use the substitution method if you want to find the two times separately, and that you draw a sketch of the graph if you are going to do some sort of symmetry argument, and ideally you're drawing the graph every time because it does give you a better understanding of what's happening.